So today we'll be discussing about the two-way. So for two-way, we just did for one-way. So in one-way scenario, we can see that eccentricity will develop either x-axis or y-axis. Like we define it either width of the foundations or length of the foundations. So what happened when you have the load neither on x nor in the y? So what you will do? Suppose instead of here, if you find the load is on that particular locations, so you can see that this one would be ex and this one would be ey, right?
EY.
So both sides you have the eccentricity. So now come back to the moment diagram. So do you have two single pen with you right now, or two sticks with you? You just take these two straight sticks or two pens in your hand, and you keep like this. You just place it like that, okay, and you hold by your finger here. Do you have it? You can demonstrate now. Do you have it in your side now?
Yes, sir.
You just hold it like that.
Yes, sir.
You take and you make 90-degree angle and you hold it like this, okay. So suppose this is your x-axis, this is your y-axis. Do you get these two sticks?
Yes, sir.
Okay, you hold it like that.
Yes, sir.
Now press on this x-axis. Suppose here, after a certain distance, now you try to press here. What is the scenario is going to happen? It try to rotates like this, right?
Yes, sir.
You understand?
Clockwise.
It's try to rotate like this. So the rotation is going to happen with respect to y-axis. Can you demonstrate by yourself? Because here is a support.
Fixed support.
Yeah, here is a support. So due to this support, it will try to rotate. While it goes down, that time this one is going down,
Yes, sir.
but y-axis rotate. Is it not?
Y-axis rotate.
Similar way,
Yes, sir.
if you apply load on this y-axis, you will find this one is try to rotate on the x-axis. Okay, based on the x-axis.
Yes, sir.
Like it will go down, y bar will go down, but the rotation will occur in x-axis if you make it fixed support here.
Sure.
Okay, so now just
Okay,
for an
sir.
example, if you want to take moment, suppose you have the eccentricity here, you want to take moment with respect to y-axis. What is your distance? Ex, right? What is the distance? Ex. So that's why we
Yes.
call my equals to p into what? P into ex. Very good. So that's why moment with respect to y-axis will be the p times ex, because the moment term is ex. Is that clear?
Yes, sir.
Okay, so similar way we can say that mx moment with respect to x-axis would be what? Now you should tell me. P must
Py into Ey.
very good. Not py, p into ey.
EY.
Same to Ey.
Yeah, same py, because this p is here. You understand? This p is here. So while you take the moment with respect to x-axis, you are having the ex, ey is the distance. While you take the moment with respect to y-axis, this is the distance, right?
Yes, sir.
Okay. So now you think that your x-axis is b-axis, width of the foundation, and your y-axis is the length of your foundations. So instead of ex, we can call it e suffix of b, right?
So
Hello?
B prime or B?
Are you getting my voice?
Yes, sir.
Okay, so while we consider the eccentricity for width directions, right, width of the foundations or footing, so that time we consider my by q ultimate, and this is the load. Okay, you can consider this is p also, but in geotechnical engineering or foundation engineering we call it, okay, q ultimate. Capital Q is for the load, smaller q is for the soil stress. And similar way you can consider for the L directions, that is your y direction. So that time moment with respect to x. Is it okay?
Yes, sir.
Okay. So here in two-way eccentricity, the major challenge is to find out the effective area, because you can see that this is not in the limitations of the only single axis. The eccentricity load can be anywhere, right? If you consider in the axis wise, it is not only lies on the axis, it lies on the any locations of the foundations, right? So that's why
Yes, sir.
the effective area can be changed randomly. Okay, so this is the major challenge to calculate, to find out the effective area. So the formula can be same. By using the Markov equations we can find out the q ultimate, but we need to find out the effective area, which is the major challenge here. Once we can find out the effective area, then we can find out the amount of what capacity, right? You know the q ultimate, but you don't know the area, so you cannot calculate how much capacity that your footing can be sustained. Okay, so that's why the researchers develop several cases. First cases is like if EL over L is greater than or equals to 1 by 6, the ratio between EL by L is greater than 1 by 6. Similarly for EB by B is greater than or equals to 1 by 6, and that situation the effective area of the of these conditions is shown in this figure, and which we call it, can you hear me?
Yes, sir.
Okay,
Yes, sir.
so if this is the situation, they find that scenario is like that, the effective area is only this, and this rest of the portion is inactive. If this is the scenario, so this effective area is look like triangle. You understand? So that time they
Yes,
are
sir.
calling this B1 and this is L1, and this is the effective area, so it's look like triangle. So what, half into base into height. So this B1 can be calculated by these equations, this L1 can be calculated by these equations. Okay, so once you get this one,
Sir, L1 is also okay, sir.
L1 is
Okay, sir. I understand, sir.
okay.
L1 is also you calculate by the same formula, sir. Half
Yes,
into base into height.
yes.
I
So
understand,
now
sir.
once you get this one, A prime, so you know the amount of area is effective. So now you can find out the another dimensions, like you exactly need what, you exactly need this B prime L prime, right? So it will give you
Yes.
A prime. So A prime you already know, right? A prime you already know from these equations. You understand or not?
Yes, sir.
Okay.
Yes, sir.
Yes, sir.
So now two are unknown, B prime or L prime. So it is not possible to find two unknown from one equations. So have a look here. They define one thing. The effective length L prime is the larger of the two dimension B1 and L1. So between B1 and L1, whichever is the larger, suppose this is will have one value B1, right? And L1 will
Yes,
have
sir.
another value. So between these two, whichever is larger, that one will consider L prime. Suppose this is 3 meter, just for an example. Suppose this is 3 meter and this is 2.5 meter. So what would be your L prime?
Sir, 3.
Three,
Very
sir.
good. So
B1.
Three, sir.
that would be your L prime, right? So once you know the L prime 3, can you find out the required amount of B for your footing?
Yes, sir.
Okay,
Yes, sir.
so
Yes, sir.
this is the way you can find out amount of B, and then you can cross check the capacity of your footing. How much capacity do you need? And then you can cross check, do you need to increase the footing or do you need to reduce the amount of load or not? So there are several cases. I will come to this picture later. There are several cases. If it is less than, the ratio is less than 0.5, and if the ratio of EB by B in between 0 to 1 by 6, that time. So that time it looks like trapezoid. Okay, it looks like trapezoid. That's why area formula is trapezoidal. And
Yes, sir.
L1 and L2, here you can see this is L2 and L1. So again, larger one would be the L prime. Between L1 and L2, larger one would be the L prime. So ultimately, we know B prime into L prime equals to A prime. So from here we can get the A prime, and from L1 to L2 we can get the L prime. So we can find out the B prime easily, right? Similar. But here you can see that this graph uses these equations, that whenever you have, we'll calculate the EL by L first, EB by B also, right? And this is also EB by B.
Required, sir.
So this is the neutral point between L2 by L ratio and L1 by L ratio. So this portion or this line is the divider. So this direction is this L2 by L1, and this direction is L1 by L2. Suppose if EL by L is 0.3, suppose, just for an example. Okay, suppose 0.3 I'm drawing, and you find that EB by B is 0.1. So that time it would be like this here. You understand or not? And then you go downward and you find this, suppose like this. Is that okay? So that would be your L2 by L1 value. And similar way, here you can go back to find out the 0.1. So 0.1 is this, right? So 0.1 is this line. So this line intersect here. So if you go down like this, maybe just here 0.6. You understand? So L1 by L2 would be, sorry, L1 by L would be 0.6. Is that clear? How can you calculate the L1 by L, L2 by L from this graph?
Yes, sir. Yes, sir.
Okay.
Sir, again, please.
Sir, again, sir.
Suppose if you have EL by L is 0.3, okay, and
Yes, sir.
EB by B is 0.1. So from this point you can see left side is L2 by L. So 0.3 you go straight, and then you select the EB by B, which is 0.1. So you selected this value, okay, and you go down and you
sir.
find this is the value. Similarly, you also select the L1 by L. Is that okay?
No, sir. It's okay.
Yes, sir.
Okay. So there are case 3 also you can check. So in the beginning on this problem, what you will do? You will first check the EL by L ratio and EB by E ratio, EB by B ratio. Then you decide on these 3 or 4 cases are here, what case you suited, right? And that case value you can apply. Okay, and finally you can practice this one. So now you should have asked me one question, sir, that how did they develop this portion, that okay, this is the effective area of this footing. How did they develop this portion? You should have asked me this question. I know you did not ask me this question, because if you ask me, I may give you another counter questions, because you studied these things in solid mechanics. Just for your understanding, I'm explaining again. Here you can see that this is a suppose footing, and this footing has a 4 corner, and you have eccentric load here, suppose, which is P, and due to this load, maybe at stress point A it is 20 compression or 10 compression, at B 25 compression, at C 15 compression, and at D 10 compression. Okay, not tension, sorry, not compression, at D. Now we can draw the stress diagram, right? So if you draw the stress diagram, here you find all the diagrams are below the what? Footing, which is compression. Only this portion is having tension. So this is our new neutral axis. Are you getting my voice? Hello?
Yes, sir.
Okay.
Yes, sir.
So this is our new neutral axis. So indirectly what? This portion of the footing is having some tension, right? Can you get my?
Sir.
Okay.
Yes, sir.
So this portion of the footing is having tension. So now the question is that how did they calculate? They calculate this stress from the combined stress calculation. There are some certain formulas to find out the each corner, or some methods to find out the each corner is stress. Then if you draw this, you'll find that okay, these portions are in having compression, okay, and but only this portion is having tension. So that's why this portion is not effective in the what? Footing, right? So this portion will be inactive portion in the footing. Are you getting the concept? So indirectly I can say this is my active portion. So if I can find out the area of this portion, that would be my active area. So that's why you can see based on the distance of this EX and EY, they develop this all the cases that you have studied now. So now we can go back to the calculation of math, right, or this numerical calculation. Okay, so this is the problem we're going to discuss. What is the problem? A square foundation is shown in figure this. Okay, so where you can see that EL is 0.3 meter, right, and EB is 0.15 meter. Okay, so assume two-way eccentricity and determine the ultimate load is Q ultimate, right? So here you can see that this is the center point of your footing. This is the center point of your footing, and this is your EL, right? This distance.
0.3 meter.
Okay, 0.3 meter, and this is your EB. Okay, that is 0.15 meter. Okay, and the dimension of the square footing is given 1.5 and 1.5. So B and L would be same, so it's easy for you. And depth DF is given how much?
Sir, 0.7, sir.
Very good, 0.7. And C prime is 0. Frictional length is given 13, and unit weight is given 18. Okay, and you see due to this load, what is the eccentricity? They denoted with the M, and this is might be the self weight. Okay,
Okay, sir.
okay, so what we need to do here, we need to find out the ultimate load. So now as per the procedure, we have seen that we need to first calculate the EL over L, EB over B. So first of all we look into it. We can find EL over L is 0.2, EB over B is 0.1. Okay, so now once you have all these values, what you need to do? You need to look into all the cases. You need to satisfy this ratio, and you can check all the cases. There are 4 or 5 cases, you can look into it. So once you find your EL by L ratio, EB by B ratio is satisfying one of the certain conditions, so that time you can decide, okay, this case you are going to use. Okay, so suppose for this one they consider actually the case 2. So because you can see that 3.2.1, right?
Yes,
This is a 3.2.1 figure. So here you can see EL
yes, sir. That was
EL by L should be less than 0.5. So EL by L is how much? EL by L is how much? 0.2, right?
Yes, sir.
0.2. And EB by B is 0.1, right?
Yes, sir.
Is it clear? 0.2 and 0.1. Okay. So now it satisfies. Is that clear to all?
Yes, sir.
Okay. So it satisfies the condition. So now we need to calculate the L1 by L, L2 by L, these two value. So
Yes, sir.
now first select the EL by L. What is the value of EL by L? 2.2, right? So this is 0.2. Is it clear? Okay.
Yes, sir.
Yes.
Suppose, as per I can draw with my mouse, maybe this is the one of my best straight line. Okay. And then EB by B.
Okay.
And EB by B, we need to select 0.1. So this is the 0.1, right?
Yes, sir. 0.2.
So now if you go straight, maybe it's just above 2, right?
Point
So
2.
it's just
Yes,
above
sir.
0.2,
2
right?
ones.
So that would be our
Yes, sir.
Yes, sir.
L2 by L. And
Yes, sir.
now look
0.2, sir.
into right side of it. Right side of it is L1 by L. So if you select the curve for 0.1, 0.1 is this one, right? No, 0.1 is this one.
No, sir.
This part, right?
Yes, sir.
This portion. So if you
Sir.
go,
0.9.
sorry, maybe little right side, right? Maybe
So,
0.85 or something,
Yes, sir.
right? Maybe here.
Yes, sir.
Yes, sir.
So this way. So now we can check.
sir, L1 by L, sir, 0.2 selection.
L2 by L.
So L1 by L is 0.85, L2 by L is 0.21. So is that okay for us according to the graph? So in exam, if you select little bit of change of it, no problem. You understand? You try to
Sir,
select by
selection of L1 by L in graph, sir. Will you go to the graph slide, sir, again?
yes.
Yes. 0.2 and sir. 1. Okay, sir. Okay, sir.
Okay.
Okay, sir.
So now can you see? We can find the value of L1 by L
Yeah.
is this much, right? And we know the L. We
Yeah.
know L is 1.5 because this is square footing. So square footing dimension is given 1.5. So you get it. So 0.85 into 1.5. So we get this L1, and we can also calculate the L2. So we know between these two, whichever is the highest, that one will consider L prime. So this would be our
L prime.
L prime.
L prime.
1.25. And based on the formula of area, we can calculate the area. So since it's the trapezoidal, we calculate the trapezoidal area. And after that, we already selected what is L prime, right? Okay. So we
Yes,
know
sir.
that since we are considering our footing or foundation would be more or like rectangular, square or something like this. So very straight away you always consider A is, or A prime is B prime into L prime, right? So we already got the value of
Yes,
L
sir.
prime, we got the value of A prime. So can you find out the B prime?
Yes.
Okay. So that is our B prime, and which will be used here. You understand?
Yes, sir.
Okay.
Yes, sir.
So now we need to use this formula, and C prime is 0. Since C prime is 0, first term of this equation would be 0. Only middle and the last term would be here. So one thing still remain to calculate the value of Q. So we can see that depth of the footing is 0.7. Depth of the footing is 0.7, right? And
Yes, sir.
we can see the unit weight is 18. So we can find out the unit weight. Stress.
Yes, sir.
Okay, and then we can find out these other values by using this phi. Okay, and then gradually, once we get all the values, we can find out the Q ultimate, and that is actually the one of the easiest way. Okay, so now do you have any confusion with this problem?
No, sir.
No problem, right?
Sir, we'll find problems, sir. When we'll do by ourselves, then so we'll find the problems.
No worry. Okay, so today I am not going to discuss any new topic, but what I'll do, I want you to practice this. Okay, so you practice this part.